We all know that the weather affects our well-being in many ways. For example, temperature, humidity, wind, and radiation affect our perception of environmental conditions. Let's try and understand how the weather elements will affect our body. One of the main physiological functions of the human body is to maintain its average internal temperature of approximately 37 degrees Celsius. The harder our thermoregulation system has to work to maintain this internal temperature, the more we perceive this as thermal discomfort, which could be heat discomfort or cold discomfort. In addition to personal factors such as clothing, activity, health, and physiological or psychological factors, the degree of thermal discomfort depends on climatic conditions, such as air temperature, wind, radiation, and humidity. To understand how all these factors work together to affect our thermoregulation system, we need to look at a so-called human energy balance model. Our body produces a lot of heat through metabolism. Additional energy is also provided by short and long wave radiation that our body absorbs. To avoid an increase of its core temperature, our body needs to get rid of superfluous heat. It does this through radiation or convection or a latent heat flow, which is referring to sweat evaporation. Also, respiration causes a heat flow from the body to the environment. If it is hot outside, then our thermoregulation system has to work hard to maintain the core temperature. It does that by increasing the skin temperature, which increases the convection and radiation rates, or by increasing the sweat rate, which facilitates evaporative cooling. Also, in cold weather, our thermoregulation system has to work hard to maintain the core temperature. It does that by decreasing the skin temperature, which reduces the convection and radiation, or through shivering, which increases the metabolic rate. High air temperatures make it difficult for the body to lose heat through convection. High humidity make it difficult for the body to lose heat through evaporation. High amounts of radiation affect the radiation balance of the body and make it difficult for it to lose heat through radiation. Low wind speeds also are an obstacle to the heat loss through convection. All of these factors together contribute to heat discomfort. On the opposite side, low temperatures facilitate the body's heat loss by convection. Low radiation shifts the radiation balance toward energy loss, and high wind speeds facilitate the heat loss by convection. All of these factors contribute to cold discomfort. A comprehensive approach that attempts to model the impact of the weather elements on our human body will consider all these energy fluxes. For practical purposes, we have often adopted very simplified models, such as the wind chill temperature index or the heat index. The wind chill temperature index indicates how cold a particular temperature feels given a certain wind speed. The chart shows an estimation of when frostbite starts if you don't protect your skin. The wind chill temperature is based on a simple calculation that only includes the two parameters, air temperature and wind speed. The calculation of the heat index appears to be slightly more complicated, but as you can see, it only depends on the two factors, air temperature and relative humidity. The combination of these two parameters gives a rough indication of how hot a temperature feels at a given humidity. The combination of these two, for example, 90-degree Fahrenheit air temperature at a relative humidity of 20% feel very warm, with a heat index somewhere between 80 and 90. However, the same temperature at 90% relative humidity lead to a heat index of approximately 120, which is perceived to be very hot. The chart shows that at very warm conditions, with a heat index between 80 and 90 degrees Fahrenheit, fatigue is possible with prolonged exposure and/or physical activity. In an extreme case, with the heat index at 130 degrees Fahrenheit or higher, heat or sunstroke is highly likely with continued exposure. A heat wave is a prolonged period of excessively hot weather. For example, during the Chicago heat wave in July 1995, people experienced air temperatures up to 106 degrees Fahrenheit that caused hundreds of people to die. In fact, more Americans die from heat-related illnesses in a typical year than from tornadoes, earthquakes, and floods together. The concept of heating degree days has been developed to have a method that will allow to evaluate energy demands to run air conditioners during hot days. As a rough estimation, the amount of heat required to maintain a certain temperature in a building is proportional to the total heating degree days. Heating degree days are calculated by comparing daily mean temperatures to a threshold of 65 degrees Fahrenheit. Each degree below 65 degrees Fahrenheit is counted as one heating degree day. For example, one day with a mean temperature of 50 degrees Fahrenheit accounts for 15 heating degree days. It comes as no surprise that the lowest number of heating degree days are in southern Florida or southern Texas. Urban landscapes affect weather patterns and temperatures. A common observation is that maximum and minimum temperatures in urban areas are higher than in nearby rural settings. This phenomenon is referred to as the urban heat island. There are several reasons for the urban heat island. Urban surfaces, consisting a lot of metal, asphalt, concrete, and stone, absorb more radiation than rural surfaces. So we would expect higher temperatures during the day and the evening. Irregular geometric shapes in a city lead to multiple reflections and absorption of radiation and lower wind speeds, which results to less removal of warm air through convection. Fossil fuel use causes additional heating. Sealed surfaces prevent water absorption and lead to less evaporative cooling. And finally, pollution over a city causes the downward redirection of outgoing long-wave radiation. All these factors cause the urban heat island that can be seen here for minimum winter temperatures in Washington, D.C.